Hello and welcome to a video presentation of my K-Play 2020 doctoral consortium paper. My name is Sylvain Daronnat, third year PhD student, and my PhD focuses on trust relationships in human-agent collaborative games. With advances in data analytics and artificial intelligence, an increasing number of virtual agents are implemented in various domains to help users make decisions. However, collaborative agents might make errors, which might affect their performance. This can decrease user trust in the agents. An important definition of trust can be found in Lee and C 2004 paper. The attitude that an agent will help achieve an individual's goals in a situation characterized by uncertainty and vulnerability. Trust is a multimodal concept, and numerous factors influence it. In 2015, Hoff and collaborators proposed to study trust by dividing it into different models, some related to our general attitude toward automation, and some others related to the system performance and behaviors. Most of the studies focused on trust in human-agent collaboration are conducted in turn-based scenarios, where the human operator can choose to take into account or discard the agent's input. The most common way of assessing trust in automated systems is through the use of survey instruments. They are administered before or after a task and consist in rating statements from low trust to high trust. However, many human-agent cooperative scenarios involve making decisions in real time, and survey instruments often fail to capture the evolution of the trust relationship over time. To study how trust evolves over time, we created a game framework inspired by an arcade classic, Missile Command. In the original game, the player is tasked with protecting cities from incoming waves of missiles. The simple yet challenging property of arcade games represents a good opportunity to create interactive human-agent collaborative tasks. Here are some footage captured from our game. Similarly to the original Missile Command, the goal of the task is to destroy incoming waves of missiles by firing explosive projectiles at them. During gameplay, the player can collaborate with an automated agent capable of assisting in the aiming task. The player can choose to leave the aiming task to the agents or override the agent's input by moving the crosshair themselves. However, only the player is able to fire a projectile. This design decision was taken in order to lessen chances of total complacency. The difficulty of the task can be modified, as well as the performance of the agent, in order to study the resulting impact on players' behavior. For more details on the design of this framework, please refer to our KAI 2019 workshop paper, accessible using the QR code displayed now. We record interaction data for different methods. One relies on survey instruments, such as standardized questionnaires about trust in automation, cognitive load, or situational awareness. The other consists of in-game logs collected during gameplay. These logs save information related to players' performance, reliance on the agent, and general gameplay elements. Using this framework, we conducted two studies, with a third one currently underway. The first study focused on agents' reliability, while the second one focused on agents' behaviors. For our first study, we examined how different levels of agents' performance and predictability influence player trust, reliance, performance, and cognitive load. To this end, we designed 4 different agents, 2 agents with high performance, and 2 agents with low performance. For every level of performance, one agent was always making errors in a more predictable way than the other. For instance, an agent's aim could always be slightly off to the right, while another would miss its shot in a less consistent manner. Our results show that participants trusted more and performed better while interacting with more predictable agents at a high level of agent performance. The same difference was not observed for low performance agents. In our second study, we tested the impact of different types of agents' errors on players' behaviors. We defined these errors using past research on human-human and human-agent interactions. In this brief showcase, you can see how these different types of errors differ from one another. Lapses happen when the agent stops working, slips when the agent becomes inaccurate, and mistakes when the agent has prioritization issues. All errors were designed to have the same impact on agent's performance. We found that mistakes were the most harmful to trust, as players thought that the agent was working against them. In addition, slips was rated as the most cognitively taxing, where lapse had the least harmful impact on players' perception of the agents. For more details, please refer to our article published at the Human Factor 2020 annual meeting. A first study is currently underway, which focuses on how visual uncertainty impacts players' perception of a collaborative agent. What I hope to gain by attending K-Play 2020 Doctoral Consortium is specific feedback from game researchers on the design of more engaging virtual agents, and how to allow human-agent communication to happen in the collaborating games, and to keep players engaged. In return, we can contribute to the Doctoral Consortium by bringing our expertise on the design of interactive tasks and how to draw insight from a mix of qualitative and quantitative data. Thank you for watching this video, and I hope to see you soon.